Hi and welcome back. In this video today we're going to be looking at ionization energy, which is our extension of atomic structure for HL. You'll remember from our SL core that we have learnt the definition of ionization energy and first ionization energy. That idea that it's the amount of energy required to remove 1 mole of electrons from 1 mole of atoms in the gaseous state. And it's really important, of course, that we remember that this is in the gaseous state because it will take energy to go from a solid or a liquid into a gas. That additional energy is beyond what we're talking about with the ionization energy. So we want the atom in the highest energy state before we start to measure the energy for the ionization. So if we were writing this as an equation, we could have something like magnesium solid going to magnesium gas plus an electron. This is going to have an energy going from solid to gas and then from gas to the loss of the electron. So the amount of energy that we would need to put in would be greater than the ionization energy. So what we want to make sure is that we have magnesium gas when we start going to magnesium gas ion plus the electron that we've lost. Then that energy that we have will of course be endothermic, because we need to put energy in, but will also be for the ionization energy alone without the change of state being added in. We don't just have first ionization energy though, okay, because we have, anytime we remove an electron, it will create an ion. So that ionization energy, if not defined as the first one, because the first ionization energy is the amount of energy required to remove the first 1 mole of electrons from the ground state, from 1 mole of gaseous atoms. So after we do that, the ionization energy will change dependent on the distance from the nucleus and, of course, the core charge. So we're going to look at the hydrogen atom again, and of course this is the emission series of hydrogen. Remember that we can tell it's an emission series by looking at the direction of the lines. So these lines are going down, so this is going from a higher to a lower energy, which means with each transition, each discrete energy jump, we will have the emission of light. So when we look at this, we know that the transition from n is equal to 1 is going from our lowest energy state, okay, and then we absorb energy up with convergence at the higher levels. If we go from 1 to infinity, then this is ionization, i.e., if we reach the highest possible level and go beyond that, we will lose the electron. The electron will have sufficient energy to leave the atom and we get ionization. So as the energy levels converge at the higher energy, we can calculate the ionization energy from what we call the convergence limit at the highest frequency. This means that given emission spectra, we can determine the ionization energy. With hydrogen, we know it contains only 1 electron, which will be in the lowest energy level when in its ground state. So then if we put in sufficient energy, the electron can be promoted to n equals infinity, i.e. it can be removed when the atom is ionized to form H+. The amount of energy here would be the same as if the energy it would emit if the electron fell from n equals infinity to n equals 1. And we know that this would produce a line in the UV spectrum. Okay, so and the UV spectrum is determined to have a wavelength of 91.2 nanometers. We can use this data to quantify the energy involved, i.e. to work out the energy that would be emitted as it falls from n equals infinity to the ground state, resulting in light of 91.2 nanometers, and therefore calculate the ionization energy. Of course, to do this, we need a couple of equations. These equations are given in your data booklet in the first couple of pages. We have C is equal to lambda V. If you've done physics, you will recognize this equation. This is the equation for the speed of light. Okay, where C is the velocity of light, lambda is the wavelength, which is given in nanometers for light. Okay, so we would have nanometers would be what we're looking for there. And then frequency of the light as well. The other equation then, linking energy to the light, is that energy is equal to Planck's constant given by h multiplied by v, which is the frequency. It's actually mu. So we can calculate the energy to remove one electron from the scenario we were given before, where we were told the frequency of the light, which was 91.2, sorry, the wavelength. So we can see here, and this has been converted to meters, so this is the conversion. 10 to the negative 9 is the meters, nanometers to meters conversion. Okay, so we have to convert that to meters to use in this equation. So we substitute in each of our values. Okay, so we have the velocity of light, which is given in your data booklet, multiplied by the frequency, multiplied by the wavelength, and we get this amount of energy. Now, this amount of energy is for 1 mole of electrons only, 1 electron only. Okay, so this is for 1 electron only. To work it out per mole, which is what the definition tells us, we need to multiply by Avogadro's number. So we take our answer in joules, multiply by Avogadro's number. This gives us the number of joules per mole, and then convert into kilojoules. So if we have a look here, we have the atomic emission spectrum of hydrogen. We're given the convergence limit, i.e. the limit to where ionization will occur, at a frequency of 3.27 times 10 to the 15 Hertz. We're asked to calculate the ionization energy for a single hydrogen atom and for 1 mole. Okay, so I want you to pause this, have a look, and then come back to see the explanation of this question. Okay, unlike our previous question, we have already been given the frequency of light. So we've already been given the frequency of the light. So remember last time we had that E is equal to Planck's constant times the frequency, but we didn't have the frequency, we'd been given the wavelength, so we needed to work out our frequency from the wavelength that we were given. More typically, you will be given the frequency. So this is a more standard question. So all we need to do is substitute in our values. So the energy for the ionization of 1 is going to be Planck's constant, which we get from our data booklet. (6.63 times 10 to the negative 34 times the frequency of the light that we get from the question. Okay, so this is 3.27 times 10 to the 15 Hertz. So then we just multiply these in, and this will give us our answer. Okay, 6.63 multiplied by 10 to the negative 34, and then we're going to multiply by 3.27 times 10 to the 15. Okay, so Hertz is actually joules per second. That's our unit there. So we get 2.17, because it's 2.168, and we're doing 3 significant figures, multiplied by 10 to the negative 18, and this is joules for per atom. Okay, this is just 1, and then we want to work per mole. So per mole, we're going to get energy is equal to 2.17 times 10 to the negative 18. And then we're going to multiply by Avogadro's number, which of course is 6.02 times 10 to the 23. When we throw those into our calculator, you're going to take our answer and we're going to multiply by Avogadro's number. We will get 1305142 joules. Okay, so now we're going to divide this by 1,000. 1, 2, 3, and we're going to make it so it's going to be 1, 2, 3, 4, 5, 6. Okay, so we're going to get 1305 kilojoules, so 1.31 times 10 to the 3 kilojoules in 3 sig figs. Okay, so that's really all we have to do for first ionization energy is these kind of questions. I have loaded up some questions for you to be able to have a look. You also need to be able to talk about first ionization energy in terms of prediction with what would be stronger, and that is essentially taking our knowledge of periodicity, effective nuclear charge, and making comparisons. So we'll go through some more questions on that in class.